Okay, welcome back for our data structure algorithm. How has we been treating you? Is it okay? Assignment 4 should be a bit easier than assignment 3. Is it okay? No, it's not. It's not. Why? Assignment 4 should be a bit easier. I think the Q simulator is a real application. We try to not only make you do data structure, we try to make it useful. The Q simulator can be clumsy, tedious, but it shouldn't be technically very hard. But then for the heap, it should be okay. I hope. Yeah. And as we mentioned before, probably the data structure and algorithm is the most difficult course in your whole whatever computer science or engineering curriculum. Okay. I hope you can tahan, and you should keep yourself a bit encouragement for that. If you survive. Okay, let's start our lecture today. Before that, let's make a few important announcements. Okay. This is a QR code. If you want to ask any question, you can also search it from the canvas. The first announcement is, you know that tomorrow is quiz 2. So it's the same thing. Please remember to bring a 2D pencil, 2B pencil. We have a bit difficulty scanning your paper last time. If you see it back later, I will talk about quiz 1. You can see the color is very light. Try to do a 2B pencil. And also maybe when you try to write word answers instead of shading the circle, you can actually try to use a pen instead. That will be easier for us to scan. So the most important thing is 2B. The scope will be week 1 to week 8, including heaps. So the other thing is your seating plan we shuffled. Last time we arranged you guys with your name. This time we arranged you with the Newsnet E number. You know you have an A number and the E number, okay? It's an E number, not the A number. So the details is there. So from E00 to 1156100, please go to this hall, okay? Otherwise, go to LT16. So that is the details, and there's more details. Please read it carefully. And most importantly, please bring your identification and also write your student ID in the quiz at that time. We have a slight problem with one of the student about the student ID, so please do not do that. Because actually, if you roll the wrong student ID, it could be an offense because you're trying to imposter another person. Okay, so please do not do that. That is very serious. Okay, so also the makeup will be next week. So we already set it up. So if you cannot come to the mix-up again, too bad. Okay, so it's already there. So the only eligible reason for makeup is MC or NS. Okay, but of course, if you have some very, very serious problem, please let us know. We will consider them by case basis. But as we already discussed in the beginning of the semester, you are not qualified for makeup if it's only personal traveling or business trip or whole activity. Okay, so please let us know. We can discuss on case basis. Second, your quiz 1 result is out. Okay, you should already receive your soft mark email. The soft mark is a place that we will see how we mark you. Okay, all the details are there. All the details of marking calculation shouldn't have much errors. But however, if you still discover any errors, please report to Turpin. He's our head TA. He will try to so-called corrective for you. But please do not treat it as a mark appeal, okay? And it's not a proposal in Chinese. 不是求分, okay? 求分 in Chinese is like ask for marks. Don't try to say, oh, my this question deserves more marks. Okay, please do not argue us with them. And also, we are not going to cater for any changes within 5 marks. Okay, because it's not going to change your marks. Because every grade in our, for example, from you to jump from B- to B, you need at least 3% or 4% totally to jump. We have a gap on every different grade. So even you say, oh, let me ask for 5 more marks in the quiz, what is it? 5% in the 100%, and each quiz is only 10%. That means you're asking for 0.05% or 0.5% in the overall. You are not going to make yourself jump a grade or something at the end of the day. You know, we are on a grade system. So a lot of data, whatever, will be lost inside. So even you try to get more 0.1%, a lot of time it doesn't help. So please understand that. Try not to struggle too much with us. Oh, this mark, that question, whatever. Okay. Yeah. And also, please do not do unreasonable appeal or verification. I know that you guys are reasonable, okay? But in the past, we do have some student anyhow. Oh, my answer should deserve more marks. And then if you ask him or her why, you don't know, I just want more marks, okay? Please do not do that. We reserve our rights to impose a penalty if you do that, okay? So please give us some reasons. For example, if you really think your expressions of your, probably the last question now, because the other marks we can correct it for you if the scanner scan your wrong answer. But if the last question, please do not argue with our markings. We already mark it very leniently. And also, only if when we mark you, we really misread your meaning. But to be honest, most of the time is students cannot express them well. There are two common problems of student answers. One problem is student answer too many things. Originally, the answer can be answered in 2 sentences. The student write a 20-sentence paragraph to explain something, okay? That is actually not a good way. And also the other thing is student answer also too many answers, as in student will give us an algorithm is ON squared, then given an algorithm is ON log N, then given a lot of things. It's like casting a net in the sea, okay? Don't do that. We don't want that. We are computer science and somehow like mathematicians. We don't want lengthy answer. It's not longer the better. Please do not do that, okay? But also it's the quiz 2 and the final. Please do not do that. Lastly, here, practical exam, okay? It's a requirement for our course to make you do coding in our data structure. Okay, we always have a struggle. Should we do more application or should we actually construct the data structure? There are 2 big schools of thoughts for data structure and algorithm course. One school of thought is we don't care about the data structure. We just use them. We just use SQL. We just use Python packages. Okay, we just use them to solve problems. It's good, but on the other hand, we need to know how to implement the data structure. How does it work internally? And if you remember our range tree, we need to augment it from time to time. So I think it's not my idea, but the departments, I mean, as in computer science department, requires student knows how to manipulate. It's like, I always use the analogy is when you are in primary 1 or 2, you need to learn how to do addition and subtraction by your hands. So you say, you can use calculator, I can use computer to calculate numbers. But sorry, at primary 1 and 2, we need to understand how addition and subtraction work, okay? So that's why we need to know how basic data structure algorithms like even linked lists or trees or hash table works in a very low level. And that's why we need to have a PE. Okay, so the PE is on 29th of October. I believe it's a Tuesday, if I don't remember it wrong. Is it Tuesday? Yeah, it's a Tuesday. Okay. Yeah, so it's a Tuesday. So Tuesday night, the timing is exactly 7 to 9, but you need to leave sometime before and after, okay? That was the exact timing for PE. You need to arrive there half an hour ago or something to sit yourself. Don't treat it as the real timing. Because, and also the other thing you may want to take note is you are going to use our own lab machine. You are not going to use our laptop. Sorry, and we blame for the AI because you know nowadays the AI, whatever, ChatGPT, whatever, some of the AI has very heavy copilot. While you say, oh, we lock down the network, how can we do that? Sorry. I don't want to tell you, but there are actually some Copilot can be used when your network is down. So we cannot prevent that. So we cannot use the normal way like Exemplify or whatever to work it on your computer. Okay, so we cannot use your own computer for PE. Please understand our limitation. So you will go to our labs. Okay, you go to our labs. We'll assign a computer for you, and you will use our lab computer. And in the lab computer, I'm sorry to say that it's only Windows machine. So for those Mac users, sorry, you have to get familiar with the Windows machine. However, in a Windows machine, I think it's also installed with Microsoft Visual Studio and Microsoft Visual Studio Code. So if you have been using Microsoft Studio Code, it's no problem because the Mac Visual Studio Code is the same as the Windows Studio Code. It's almost the same. Okay, so you don't have to worry too much about that if you're using Microsoft Visual Code. Okay, Visual Studio Code. So we have more details, and we will have some past paper in there. Usually, all our PE has 3 parts. The first part is very simple. Usually, it's linked list. Second part is normal. Usually, is some of your assignment 2 to 4, assignment 2 to 5 variation. For example, I will ask you to do a heap. Okay, but the heap you have modified it. I think 1 year the heap is I asked you to modify it to, instead of binary heap, modify to a ternary heap, which means every heap node have 3 children. Okay. The third one, we are supposed for A+ student. So the last one usually is difficult. Okay, so don't think that you can answer all. And lastly, is a bad news. Usually our PE average is about 30 marks out of 100. Okay, so don't expect too high marks in PE because we also understand PE is very high pressured, stressful, 2 hours, you need to finish a lot of coding, strategize yourself, and don't try to think, oh, if I cannot answer all 3 parts completely 100%, I'm rubbish, I'm doomed. Don't think about that, okay? The PE marks usually we gear at the average is of 30 marks, which means average is about 1 part only. 3 parts, you can answer 1 part, you're already at average, okay? So we'll talk more about the PE next week. So let's have more information. Okay, let's start. Last week we talked about heap and priority. Today we talk about one last form of trees in our course. It's called union find. We usually call the whole data structure disjoint set. You know set. I hope you know. Remember what set? Disjoint means I have many sets, but they don't have common element. Okay, so let's talk about some application. It's not very present, but if you remember, there was a time we are in COVID time, especially in Singapore, we have this tracing. Remember the little dongle things? What does that do? What does that do? Actually, it creates a network that if you go for search for it, they do have a web page, real-time recording, things like that. Okay. What does it mean is how do the people got infected, connected? And this graph usually they use a real-time connection. However, one important queries in this chart is actually I only want to know one thing. Are 2 persons connected? This is the ultimate goal of this data structure. Are they connected? I don't care how are they connected. Is it okay? I don't care you contact him contact another person. I don't care about who are in the middle one. I just know that if these 2 persons have a chain of connection. Is it okay? Does it make sense? Okay. So I just need if 2 of the nodes are connected. For example, you can see that here, this node over here, this one I can drag it over. Okay, I can drag it out. This node is not connected to this one. You can see that, right? One is in one cluster, the other is another cluster. But this node here is connected to this one. Is it okay? So can you understand? So we want to ask about this data structure. I just give you any of these two nodes. Are they connected? You can have multiple chains of connection, but I just need to know, are they connected? This is where the COVID tracing was at that time. This is one of the application of our data structure. The other one is, actually there's a lot of data structure. If you have a very complicated maze, what I want to know is if I give you any two positions, usually maze have one entrance and one exit. I don't want that. What I want to do is in any part of the maze, I arbitrarily take two places. And I want to know if these two places have a path between them. Can I go from X to Y? But I don't need to know the path. I only know, is it possible? I only want to answer the answer. Okay, how do I do that? For example, can you go to X to Y? On top of that, we have one more allowed operation. For example, this is the first step, right? I want to process the maze so that I ask if any 2 points are connected. Can you go from Y to Z here? However, there's one more operation I can do. For example, in the maze, the drawing is not accurate, okay? I already know all the places in B can connect to each other. It's not correctly drawn, okay? Here. So there's a region in the maze. I know that everywhere can connect to everywhere. A part, everywhere in A can connect to A, okay? So we actually know certain region they are compartmentalized, or we call it partitioned, the space. So a maze have this different region. What is the operation? The operation is, what if you are allowed to knock down a wall? So for example, A is not connected to C, right? The things in A, the position in A cannot go to C. But what if I knock down a door? For example, I want to destroy a wall. If I want to destroy a wall between B and F, then anywhere in B can go to F, and these two areas become one union area. So when before that, when I ask, can somewhere here go to somewhere here? And you already know that B is one region, cannot go to other places. F is one region, cannot go to another places. You already know that, oh, these 2 points are not connected. However, if I use the so-called the wall destruction power, I destruct a wall between B and F, then B is one area. Then I ask again, just now the two positions, are they connected? Then this time is yes. So we want to construct a data structure like that. The operation are two very simple things. One is, are they connected? Second is, I can join two areas. So if you talk about a maze, this is a very small maze, 3 by 3. This is like a very, very big maze, right? In the beginning, I can decompose the maze into very little grids. For example, if this is the very small maze, I only have 9 positions. And I assume each of the position is the isolated rooms of cells. A cannot go to B because it's totally walled up. C is a wall, is totally isolated. So if you are being put into C, you cannot go everywhere. And this is where the definition of disjoint set. In here, I represent a set containing a cell if they can go to others. Okay, so that means in the beginning, because every cell is an island, Oh, sorry, I didn't talk about the cell set. So what I do is, if I can destroy the wall between E and F, that means I build a tunnel between them. Okay, not only because you don't only destroy the wall, you want to connect this one. Maybe you don't destroy the wall. I do some connection between E and F, then E and F is connected. I can connect I to G. You say, how do I connect I to G? Maybe in the cell I, you take a tunnel, go to G. Okay, you bypass H and go to G, and you also connect E to D. Now D can go to E, E can go to F, I can go to G. And I also connect A to B. And now what you want to ask, can I go from G to D? Are they connected? The operation is called find, okay? G connected to D. But you see here, G is only connected to I, D is only connected to E to F. So if you are dropped in the position D, you cannot go to G. And I can do more dynamically, connect more cell. For example, now I connect D to F, which is the same thing. I can connect B, because when I connect D to F now, oh, sorry, I'm not connected, I find. I'm asking, is D is connected to F? But you can see D can go to E, can go to F. So if I ask if D can connect to F, it's true. Now I add more connection. I add B to C. I add H to E. I add A to C. I add F to I. After I add more connections, I ask now again the same question. Is G connected to D? Now the situation changed, because D can go to E, can go to F, can go to I, can go to G now. So G is connected to D. Okay. And what happened is, we want to impose this we call transitivity. If any P is connected to Q and Q is connected to R, we means P is connected to R. Remember last time we talked about the transitive relationship? You love your girlfriend loves her father. It doesn't mean you love her father. There's no transitivity. But if have transitivity, that means you also have to love his father. His father also have to love you. Okay, that's called transitivity. So transitivity means if P is connected to G, P is connected to Q, Q is connected to R, P is connected to R. That's called transitivity. Yeah, and we connected all the maximal mutually exclusive. Okay, so what we do is we actually represent each connected component as a set. That's why this data structure is called disjoint set. In the beginning, before anything is connected, you can imagine there were 9 sets, and each set contains only one letter. One set only contains A, one set only contains B. And when you want to join 2 sets, for example, now you have 3 components, right? A, B, C is one connected set. D, E, F, H is one connected set. G, I is one connected set. Go back to our operations. What do you mean by union them? Union them, okay? If I say I want to connect G to H, that's why this operation is called union. I union G to H, but I don't only union the elements of G to H. I union the sets that contain G, which is GI, and the set that contain H, which is DEFH, to union them and become a larger connected component. Okay, so after I connect G to H, my maze have 2 connected components. That means if I am in the position A, I can go to B to C. But if I am in the position A, I cannot go to position E. So there are 2 connected components. I can further union. So the disjoint set structure is like that. First, you use a constructor to construct the number of cells, or A, B, C, D, E. In that case, it's 9. And then find is asking if 2 of the items are connected. And unions means I want to join the set that contain P with the set that contain Q. There are 2 situations. First is P and Q are in two different sets. You have to union them. But the second one is P and Q could be already in the same set. Then you do nothing. Okay. So let's talk about how do we propose some algorithm of doing this. We represent the objects by the numbers. For example, if I have 9 objects, I can name the objects 0, 1, 2, 3, 4, 5, 6, 7, 8. And one of the easiest way to recognize it is called this. Let's move that way. This algorithm is called quick find. What's quick find? Very easy. If they're in the same component, I give them a label, right? Graphically, you see the lower graph. 0, 6, 4 is component A. 1, 7, 2, 5 are component B. 3 and 8 are component C. Very simple. I just in the array for each object, I give them the component identifier. Very simple, right? So this is called quick find. I just use an extra array to contain the component identifier. Okay, now how do I do find? How do I search for if 2 objects P and Qs are in the same component? Very simple. I find the component identifier, right? So for example, if I find 1 and 2, are they in the same component? The component ID for, this one is, the component ID for 1 is B. The component ID for 2 is also B, then it's the same, okay? But of course, this one is, we just change the translation because instead of using ABC, I use numbers. Okay, so component 0, component 1, and 3. So we can actually use number to represent the component instead of using letters. So if you want to find if 2 objects are in the same component, you just have to retrieve their component ID. For example, can I ask if 6 and 7 are in the same component? The component ID for 6 is 0. The component ID for 7 is 1. Too bad, they're not in the same component, okay? So this is called quick find, because if you set up this data structure, if you want to find if 2 items are in the same component, what is the time complexity? 1. You don't need any operations. You directly retrieve for the component number, right? Super fast. What is the problem? The problem is, the problem is union. So in the first place, every item is an island. So every item from 0 to 9, 0 to 8 is, each of them are isolated. If I need to union 2 of the items, for example, I want to union P to Q, sorry, I have to go over all the items in the array to update the component. For example, now I want to union 4 to 1. I need to go to all items that is originally 4 to change it to 1. You say very fast, right? How about a union 1 to 3? Okay, now 1 to 3. A union. If I union 2 to 3 now, you see how many numbers I need to update? I need to update the rest of all of them to be component 2. So this way, now if you can see that if I want to connect 5, 7, 8, so 5, 7, 8 can be one component. But if I want to connect 5, 8, 7 into this one, I need to update all the numbers. So the problem of quick find is the updating needs O(n) time. Union operation of the quick find needs O(n) time, which is totally not acceptable. Okay. On the other hand, I would like you to change your mind a bit. Remember that each object will belongs to one component, and the component have an identifier. Let's choose the identifier to be one of its elements. For example, now 1, 2, 3, 4 are in the same component. and I choose one of the item as the identifier. So for example, I choose 2. So 1, 2, 3, 1, 3, 4, and 2 all belongs to component 2. And instead of just array, I treat them as a tree. What do you mean? Whoever you have the component ID, you are thinking that you are actually a child of that node. So you can think that it's a flat tree. So if I want to union 6 and 7, 6 and 7 will choose one of the component to be its root of the tree. For example, if I choose 7 union, if I want to union the 6, 7, and the 2 together, I choose one of them. For example, I choose 2. So all the objects 1, 2, 3, 4, 6, 7 will have the component ID as 2, and I imagine that it's like a flat tree. So every number will point to its root. Of course, it's still the flat quick find data function. So the running time of that, oh sorry, I already gave you. The spoiler of find and union will be O1 and ON. That means finding 2 objects are they connected is very fast, O1. But then if you need to update everything, you don't only need to scan all the items in that component. You actually have to scan the whole array. Otherwise, for example here, how do you know 6 and 7 are the only 2 items in component 7 before? You need to take out all the items in the whole arrays which belongs to component 7. So you have to search. Okay, so it's very dumb. So we don't want to do that. But why do we introduce that? Because actually this gives you some hints for a better structure. If you can imagine this a tree, let's do the next data structure. So let's just a conclusion first. Quick find, you just need to find the component ID and compare if they are in the same component. Okay, quick find, the union is a bit dumb. You have to search for the whole array for the same component to update the component ID. Let's do another called quick union. Actually, think about that. If the component ID can be indicate who is your parent, you don't only have to point to your root. These 2 are actually 3 components in our graph, but they're being represented by a tree. The component ID now become parents. So that means object 0 is pointing to 6 from the first beginning. Object 4 is pointing to 6. 6 is pointing to 6. And these 3 will actually assembled to be one component in this disjoint set. And you can see that 3 is pointing to 3 as another component. But the interesting thing is 7. 7 is the long tree. 5 is pointing to 1. 1 is pointing to 2. 2 is pointing to 7, and so on. And all of them is concluded they're in component 7. This is called quick union. Why is it quick union? First of all, how do I tell if any P and Q are in the same component? I find their parents. Okay. Or is there an example here? For example, if I want to ask is 4 and 1 are in the same component, what do I do? For 4, I find its parent. 4 is ultimate root parent is 6. 1's ultimate root parent is 7 because 1 go to 2, 2 go to 7. And then you can ask is 6 equal to 7 because it's the root of the component. Too bad, false. But if you want to ask is 1 the same component as 8? 1's root is 7, 8's root is also 7. That's why they're the same. So this find operation, instead of just find one component like quick find, we have to look to the parents. So you just find from any of the node, go up to find the root and compare if the root are the same. How about union? Union is a bit easier now. You don't have to go through the whole array because what you need to do is you find the parents. which means the root of the two components. And then you union those two only. Okay, for example, if I want to union the set of 4 and the set of 1, what should I do? The set of 4 has a root 6. The set of 1 has a root 7. Now the union operation will do the following. I only need to connect the parent of 7 is 6. That's it. Okay. So the union only need to link 2 nodes, become a bigger tree. Like that. And you can see the good things somehow is the original 0 and 4 are in component 6. But how about original 7 sets? All the members of 1, 2, and 8 do not have to be updated because I only need to say 7 has a parent of 6. Okay, so this is the quick union. But the question is it really quick? Let's see. Now I have all these 9 sets. If I want to union 2 of them, let's say I want to union 3 and 4, I put 3 as the child of 4. I union 4 to 9. Because I need to union 4, 3, and 9 together, I directly put 4 as the child of 9. I union 8 and 0. I union 2 to 3. 3 is in this set over here, and I put 2 together. I union 5 to 6. I union, continue, I union 5 to 9. So this set of 5, 6 have to union with the 9 and 6. What you do is you get the parent, which the root, which is 6 and 9, you just put it under. Union 7 and 3, 7 put under 3. 3 is having the root of 9. And then now you union 4 and 8. Wow, this is serious. Because 8 have this 3, 4 have this big 3. You put the 3 unders and so on. So you union the things by finding their root and just join the root together. So there's a union. Okay, you can see for P and Q, I find the ultimate parent by P is equal to parent P. And Q also find the ultimate parent, which is the root, and just link one of the parent to is another root. What is the time complexity? What is the worst case? For finding what is the time spent for? The spend time for from any of the node, you have to travel all the way to the root, right? How many nodes will be there? Worst case. Worst case is when you have some mysterious operation, you actually link up the whole tree in a linear linked list manner. Then it becomes ON. But if this algorithm is called quick union, is union faster? The time you merge 2 sets is very fast, O1. But don't remember, you need to find the root. When you need to find the both root, it's still ON. So we are not helping. The final conclusion of this so-called quick unions is even worse. Findings need ON, unions need ON. Okay, but am I pulling your legs, telling you a worse algorithm? Because we can do something clever. Okay, so anyway, this is the conclusion of quick union and quick union in quick union and find in quick union. So the summary is, if this quick find is fast, union is expensive. Quick union is if the tree is too tall and unbalanced, both of them will conclude in ON. So let's try to optimize it. Go to our quick union, the last algorithm. Actually, at the last steps, when you want to union this tree to tree, let's say you already know the root 7 and the root 6. How should you make them parents of which one? Do you want to join this tree like this? or this? And why? Which way you think, or at least artistically you feel is better? Who think the purple one is better? Who think the brown one is better? Why you think the purple one are better? It looks like what? It looks like more flat, right? And you can see that the height of one become height 2, one become height 3. Okay, now can we join the tree depends on the height? It's a bit difficult, okay? Because you cannot maintain the height like the binary search tree. So what should we do? So what we want to do is we depend on the size of the tree. How many nodes are there in the tree? So what we do is the left tree has 5 nodes. The right tree has 3 nodes. We want to put the tree with less node under the tree with more nodes. Okay, so there's a code. It's a bit so-called complicated. Actually, it's very simple. It's like before, you find the root P and Q, but you ask if size P, the root P is more than Q, then Q will go under P because the parent of Q is P. Otherwise, it's a reverse. So what you do is you join the tree with less node under the root of the tree with more node. Does that matter? Let's try. So for example, this one, if you want to union 1 to 4, you put 6 under 7. Like that, instead of 7 under 6. Let's see, is this better? This is the same operation just now we did in the last operation examples. Now I join 3 to 4. But you say, oh, if 3 to 4, they have the same node, doesn't matter lah. Okay, I can put 4 as the parents of 3 or 3 as the parents of 4. It doesn't matter. Now I want to join 4 to 9. Now it matters. 3, 4 have 2 nodes. 9 only have 1 node. So 9 has less power. So 4 wins. 4 is the ultimate root. You put 9 under 4. Now I want to join 8 and 0. Both of them, 8 and 0 are 1 node, so it doesn't matter. Now I want to join 2, 3. 2 is a singleton. So it's less power. So 2 has to put under 4 instead because the tree of 4 has 3 nodes. Now I put 5 to 6 and continue. I put 5 to 9. The number of nodes in 5 is 2 because if the node 5 and 6, the number of nodes in 9 is 4 because it's 4, 2, 3, 9, 4 nodes. So I put 6 under 4. Now I union 7 and 3. 7 had to put under 4 because 7 has fewer nodes. I put 4 to 8. Wow, which one is less? 0, 8 has less node, right? So 0, 8 had to put under 4. And now I union lastly 1 and whatever. Do you see the tree is a lot flatter this time? So this is the tree, we called it using what we call the weighted union. Weighted unions means you put the tree with less node under the parents of the tree with more nodes. This is what we had compared to last one. This is the last one. Do you see that? The last tree, we did it before the weighted union, is very tall. And come back to this. This is what the tree we use for weighted union is a lot flatter. Flatter means the height of the tree is a lot shorter. But how short? What is the maximum depth of this tree? Well, a wild guess is, do you think it will be ON? Of course, we have to have some improvement, right? The maximum of depth of this tree under the weighted union will be a log N. Here is the proof, and I'm not going through it today. I think the math is too complicated. basically you are going through induction again. Okay, so you just need to do induction, saying that all the trees is before that is ON log n, and then you add one more trees and so on. Okay, so I'm not going through the proof. If you're interested, go through the proof. But what I want to say that is under weighted union, the conclusion is the tree of the whole disjoint set will be less than ON. So if it's O log n, what will be the running time of the find and union? Remember, find and union, you always go from any node to the root. And if your tree height is bounded by log n, that means you improve the algorithm to log n. Every find and every union operation can be log n. So this is our new algorithm with the weighted union. You find the root, and instead of anyhow put one of the other's parent, you compare the size. I only put the fewer node tree under the one we pick up. Okay. This is one of our summary of our second last algorithm of find union find log n. Are we satisfied with that? No, we want to improve more. Okay, how? Improvement. How to prove improvement is not a good thing, but let me introduce the improvement is instead of having a nice queue, the improvement is cut queue. I don't care, cut queues. What is the difference between this and this? Of course, you say the last one is very unordered, right? And in Singapore, it's a sin, right? Because Singapore is a very older country. You must be in the queue. And we go on the bus one by one. I'm sorry. Now I'm suggesting is everyone just go to the gates and crowd there and get on the bus. I think it's actually a bit like our NUS school bus, right? Do our NUS school bus have a queue? No. When there's a lot of people, everyone just try to crowd to the gate and get up the bus. Actually, if I ask you, do you think this way is faster or like our SRS whatever the Singapore bus terminal, you actually queue up? Which one is faster? If you have a lot of people, I dare not to say, but actually cutting queue may be faster. Of all the people fish on bus, let's see why. So we introduce a new way of doing this. Provided that we have all those weighted union way of operation for our disjoint set, we introduce a new rules. When we do the find or any operation to find things, like I want to look for something 11. For example, I want to see whether 11 is in the same set with another item 32. Let's don't care about 32 first. When I'm looking for 11, I need to travel from 11 to 9, 11 to 6, 6 to 1, to 2 to 7, right? After I find that, oh, I know that the root of this tree is 7. But before I do anything else, I do a very bizarre things. I cut queue. What does it mean? Anyone on this ancestor root of the red node, all pointed to 7. Is it okay? But you say, can 7 have so many children? Doesn't matter. We don't record the children. If you remember, all the node just remember who are their parents. All the node do not remember who are their children. Because whenever you do finding, whenever you do union, it's different from a binary search tree. Binary search tree is always coming from the root to go down. But our disjoint set is always coming from the leaf or the internal node to move up to the root. So we don't have to care about how many children does every node has, but every node has one parent. So again, let me repeat. Whatever you do any operation on a node like 11, you will go to the root. Any node that you travel on the route. During that operation, I will make them all point to the route. That's it. Does it help? So find root is all the root. Originally is all the root is equal to the parent root. And whether all the root, I will actually point to the parent. I will actually change them. Yeah. So but on the other hand, there's a simpler one is I just point to the grandpa. This is another variation. So how fast can it be? Here comes to what you don't want to know. If you don't want to know the proof before, you don't want to know this. The theorem by Targent in 1975 is, if you do this, any sequence of m union find operation on n objects takes n plus m times alpha mn time. Wow, what is that? So that means if you have n objects, you need this. If your m is close to n, O(n) plus m alpha whatsoever is the total time. Before we go on, if you average its operation, that means it's very cheap. It's almost O1. What is this alpha function? This alpha function is a new mathematical definition called inverse Ackermann function, in which, be careful, the n will make the function increase very slowly. If n is 4, Ackermann, this IA function will become 0. If n is 8, it's 1. If n is 32, it's 2. That means even if you have 2 to power 65,000 objects, this Ackermann function is only 4. That means, yeah, this Ackermann function is not constant, but it's a very pathetically increasing constant. It only increased like that very little bit. So we can almost treat this inverse Ackermann function as a constant function. And then if it's almost constant, that means the sequence of m unions and n object takes n plus m time always, almost. Huh? And if you average it out for the m operation and n object, that means each one take O1 time. What is the proof? Sorry, I'm going to give you the proof, okay? The proof can take 2 lectures. Okay, so let's do a miracle of curve. This is what I got it from another comics. Yeah, this is a comic for that. If you know that there's some comics for math, this is a comic for math. It's talking about all these very difficult things, okay? But what I don't need you to do a proof. But of course, if you're very mathematically inclined, please go ahead to try to read the proof. Yeah. So the proof is very difficult, but the algorithm itself is very simple to implement. There was one time we actually even put it in the PE, and I think the rate of success is quite high on that year. Okay, yeah. So the theorem is, can we do even better? I think the proof, actually we have another proof we cannot do even better. So the weighted union with path compression is one of the best bound exists so far. Okay, so this is our summary today. The first algorithm is doing quick find. Finding is O1, union is ON. We did a worse improvement. That means we tried to do it so-called better. We improve it to quick union, but the find and union will worsen to ON and ON. But because of the quick union, we have an idea is like a tree. So we actually do the weighted union from the quick union. That means we put the tree with lesser node under the root of the tree with more node, and that improves our algorithm to log n. And if we cut Q, that means we still do weighted union, but in the midst of do finding and union, when you actually compress the path, we can actually almost achieve Ackermann MN, which that means each of the find operation and union operation, you will close to constant time. However, this is an amortized cost. As we said, like last time, our hash table resizing, you may have sometimes you do a big path compression of a very long path and you take a lot of time. But it's only a compression one, because once your path is compressed, later you actually search any node on that path will be totally O1. So this path compression, we call it something called amortized. Amortized means you average out the total time. Okay, so it's called amortized reanalysis. And of course, we are only talking about joining space. That means I have two, like the maze, right? I join them, I join them, I join them. If I have all these sets, I keep joining them. What if you want to split them? That means, for example, if you talk about the COVID tracing, you have all these connection between the patients, but somehow in the midst of it, you find that, oh, one connection is false. This person actually didn't connect the other person. It's just don't know, somehow his dongle, the tracking machine, somehow he didn't carry around or whatever. It dropped to other person and show that it's connected to that person. So we want to break some condition by splitting the set. How can we do that? This is another paper in 2013, how to do dynamic graph connectivity in O log n OON square root time. Okay, there's some other consideration, but it's splitting. But of course, we don't talk about splitting. In this course, we only require you to do joining. Okay, so today is a bit fast. What is the application? For example, in a maze, you want to see whether two places are connected. And especially nowadays, we do a lot of AI generation game. For example, the maze, I don't know, anyone play Diablo? Anyone play Diablo? You know the Diablo maze, at least I know that Diablo 2 is automatically generated. That means the maze are randomly generated. So can you tell whether two places are connected? Games is more like a bigger state. Can you connect it to each other? But more practical application is like network. Can you tell if two network clusters are connected to each other? Or actually, if you use a split, if some of the connection fail, can you ensure your whole network is still connected? This actually related to your security and also network robustness. Why? For some network, you want them to be connected even if some computer failure. But for you, some of them are you from InfoSec, right? You want some network can be disconnected quickly by one or two computers. Cut off. For example, if there's some attack, you know that, you cut off some of the connection and you prevent the attack. So how do you know the network connectivity? Yeah. The other one, I think, is what is the least common ancestor? That means if you have a family tree, you want to know if two members are in the same family, instead of finding their most top ancestor, you want to find who is the closest common ancestor. For example, let's say if you believe in Christianity, we all from Adam and Eve. Let's imagine that, okay? Well, I'm not preaching. Let's talk about, so you can see our family tree all trace back to that, but doesn't mean me and you, the common ancestor is Adam and Eve. Maybe in the middle, maybe in year 1000 AD 1000, we have a common ancestor. Actually, we are brothers and sisters, okay, if according to Christianity. So we have some common ancestor. Not only, you do not have to trace back to Adam and Eve. You may have some common ancestor when you and our parents just arrived to Asia or whatsoever, okay? So we can have some common ancestor. So this means, if a large tree, can you just find the common ancestor? Okay. So there's other things like programming languages. You have other like image processing in MATLAB, physics. You have other things that this union foundation structure is very possible. There's one more related to my research. This is actually my PhD thesis. We talk about DNAs, molecules. One of the interesting things about molecules is some of the molecules actually interact with each other highly related to its geometric shape. For example, some of the molecule actually acting up, I don't know whether you know about drugs. Some virus is like a Pac-Man, and your cell, you eat up, right? You know the COVID virus have all this plug and socket mechanism. So for how do you make some drugs is you fill up the socket. And some of the molecules like this one is called gramoside A, it's like a tunnel. So what does it mean is the molecule is like that. This is the sideway. But if you look through this one here, actually you have a hole there. Some molecules are like that. And what does this molecule do? This is kind of some enzymes. That means some of the other chemicals will go into this tunnel. That means walk through this tunnel. And in the middle, go through the tunnel, it performs something. It changes the matter whatsoever. It's quite interesting. Okay? But then the big question is, if you can have some model of this DNA molecules or whatever enzymes, how do you detect the tunnel? But you say very simple, I just see, right? But then you can see there's actually other tunnels. For example, if you reduce the atomic size, you have other tunnels. How do you find the biggest tunnel? What does it deal with union find? A tunnel in a molecule is actually a connected space in the empty space. That means this portion of space is actually connected to this portion of space is actually connected to this portion of space. So you can actually do geometric computation to triangulate the space and find the tunnel automatically. And in mathematics, there's this term called Betti number. Anyone called Betti here? Betti, B-E-T-T-I, is talking about how do you mathematically describe a shape, have how many tunnels or torus. If you notice that, anyone eat donuts? Donuts have a tunnel. Donuts have a hole, right? So that kind of things is how you can detect it in geometric shape that you use highly using this union shape. Okay. Okay. So that's it. Today is a bit short because next topic is the graph. So I do not want to start the graph totally together. And I will just stop here today. Today will be short. Last year is the same. Okay. Okay. So no question. And today we have a faster release. Remember, for those latecomers, we have 3 important announcements on our quiz tomorrow, on our quiz we just announced, and the PE. Please go to rewatch the video for the first 5 minutes if you came late today, okay? Thank you.